induce a larger storage. This is the difference. So dams are conceived for storing a lot of water, for storing water for a long time. What is then the purpose for building a dam? The purpose is to compensate the natural variability of river flows, to ensure a fairly constant withdrawal. Dams are conceived in order to store water where we don't need it and to release water after storing it when we need water. So the purpose of a dam is to create a large storage. The storage in river barrages is much smaller. River barrages can ensure some compensation, but not in the long term. If they can provide some compensation, is normally limited to 24 hours when I talk about barrages. In dams, the compensation is seasonal. Usually we accumulate water during the winter and release it during the summer. For barrages, the volume is much smaller. As a consequence, dams are more important infrastructures with respect to barrages. Barrages are smaller infrastructures. Typically, they are built over small rivers, not only, but typically over small rivers. Keep in mind that there are some exceptions on the purpose of barrages. Some of them may be built just for stabilizing the riverbed, not necessarily for withdrawing water. Some of them may be built for ensuring navigation, so keeping the water level at a measure that allows navigation. But the great majority of barrages are coupled with some withdrawal facilities. Now, in order to establish by law the difference between the two, because it's extremely important for administration that we make an objective difference between barrages and dams, the Italian law in force adopt a criteria that is based on two indicators. And the first indicator is that, let me see if it's already here. No. In Italy, dams are defined as structures that are either more than 15 meters high, and the measure is taken by the top from the bottom of the foundations. So if a transversal structure exceeds 15 meters of height, it's a dam, or either more than 15 meters height, or originating an upstream storage of more than 1 million cubic meters. So if you have one of these two conditions that is met, then we are talking about a dam. And this means that the structure is under the remits of the National Authority for Dams. And the National Authority for Dams prescribes that a continuous and very detailed monitoring is carried out, is ensured for the structure itself. The reason is clear. If you have a structure that stores more than 1 million cubic meters of water or is taller than 15 meters, it's potentially dangerous. In case of a collapse, of course, you induce downstream a potential danger, and for this reason needs to be monitored and needs to be surveilled with very specific regulations. You can say that this classification is a bit strange, because if the storage is 99999, then it's not considered to be dangerous. If it is 1 million, then it's dangerous. But still you need a threshold, you need a a line of separation between structures that need to be carefully monitored and structures that need less monitoring. So, we don't talk about dams here, we talk about barrages. What is the reason? The reason is very simple. First, barrages require a dedicated subject, a dedicated university course. Dams, sorry. Dams are more complicated. They require a dedicated university course. But there is also a very practical reason. Today, it's very, very rare, very infrequent that engineers get an opportunity to design a dam, because most of the dams that were considered to be efficient and convenient, economically convenient, have been already built. And especially if you work in the Western world, there are still dams that are under construction in the East and in Asia. They are building a lot of dams, and the reason is that in the past they couldn't have the opportunity for political tensions or for economic situation that didn't allow the investment of the large amount of money that is needed to build a dam. Conversely, river barrages are built very frequently today, because today there is a lot of interest in renewable energy, renewable electricity. And the reason is clear, because we want to minimize carbon emissions. And renewable electricity, one very interesting resource is given by small hydropower plants. And the small hydropower plants can be built just by realizing a small river barrage. And this is why there is a lot of requests to professional engineers to design this type of barrages today. Keep in mind that when we talk about barrages, I mentioned that some of them are built with the only purpose of stabilizing the riverbed. Usually in this case, we don't call them barrages, we call them check dams. If the only purpose is to fix, to stabilize the riverbed, then we talk about check dams. And barrages are intended, we define barrages, the structures that are intended to withdraw the dry water. I just want to give you an idea of, here there is a picture. And this is a typical barrage. You see that there is a transversal structure that creates upstream some storage, and then you have water that can flow by surmounting a gate here. The gate is placed here, and this is what is called a weir. It's a threshold that once it's exceeded by water, then water can flow downstream. And water can flow downstream also by flowing through a bottom discharge. These bottom discharges are called sluiceways. So the weirs are the water flows, the water, let me call it apertures, that are placed, are passed because the water level gets above a threshold. When you have a flow of water from the bottom, then it's called sluiceway, and it can be regulated or not. In this case, it's not clear to me if it's regulated or not. If there is a gate that can move up and down, then it's regulated. If there are only windows with no gates in the bottom, they are called sluiceways. And I can show you some other pictures. Let me check here. Briglia is the Italian word for a check dam. Just one second. Here is another example. This is a check dam, and you see that there is a wall with a passage of water here, and this is typically a check dam. The only purpose here is just to stabilize the level of the riverbed. The riverbed is stabilized because you have sedimentation upstream, and therefore the riverbed get at the fixed level of the check dam here. And these passages are normally built in order to concentrate the low flow in a small portion of the river. And the reason is that they want to make easier the migration of fishes upstream. If you concentrate the low flow in a small portion of the river, then the fishes can find a way to get upstream the barrage. Let me see if we can have. These are pictures of check dams again. Let me see. This is another example on a small river. Not very visible, but this is an old check dam. And in this case, again, this is a check dam and not a barrage, but their structure is very similar. In this case, you have the crest of the check dam that is lowered in the middle. And in this case, this is done not for the purpose of allowing migration of fishes. In this case, it's done because they wanted to keep the water flow far from the sides of the river, from the hill slopes, in order to avoid erosion at the toe of the hill slope, because you know that erosion at the toe of an hill slope can originate landslides. And therefore you will see that even river barrages sometimes adopt this solution. They have a concentration of the flow in the middle of the river, which is coupled with a fish ramp in order to allow fishes to migrate upstream. Okay, and instead, if I look for the Italian term traversa fluviale maybe, because otherwise it's too... Okay, we get this one, which we already saw, but this one is interesting. Okay, this one is an interesting example, and you see this is a barrage with windows, gates in the middle, and the fish ramp on the left. You see this long channel on the left is a fish ramp, and here it's equipped with gates, mobile gates, which are maneuvered by devices that are placed over this beam, top beam, and by pulling from the top beam the gates, they regulate the outflow from this barrage. I wanted to give you. Okay, let's concentrate on the figure on my webpage, which I think they are informative enough. Okay, and on my webpage you can find this image from Google Earth, which can be magnified. You can zoom it. And this is a barrage that is built on the Danube River. On the Danube River, the main purpose of this barrage is to ensure navigation, but it is also used for producing hydropower. And if we enlarge it, we can clearly recognize some key features. For instance, here, this is the hydropower plant. And these are the gates through which water flows to produce hydropower. It's very simple. Basically, there are turbines that are moved by the flowing water. And this is a symmetric structure, so even on the other side there is a hydropower plant. And the reason why they use the two plants is that they are, the Danube here is, on the two sides there are two different states. I don't remember what they are, it is written in the web page, and therefore they wanted for each state its own hydropower plant. This one that you see here is the navigation lock. So this channel is the navigation lock. The navigation lock allows ships to move upstream and downstream. And the way they allow the ship to move upstream and downstream, it's through an alternative opening of gates that are placed upstream and downstream. And I will show you a sketch later on. And you see the gates downstream are gates called Porte Vinciane. They are gates that close in this way. And in this way they can use the pressure of water to keep the gate closed. This is an example of a very complicated infrastructure. We will not focus on this complicated infrastructure. We will focus on barrages with no regulation. So barrages that are not equipped with automatic regulation gates. And these are the barrages that are typically realized on large rivers. We will focus on small barrages for small rivers, which are more frequent and more frequently built. Keep in mind that these barrages on large rivers, which again are built essentially for allowing navigation, have a strong impact on the ecology of the river itself. And the reason is that you basically make the flow of water slower, and therefore the exchange of water into the river becomes slower, and therefore there is an impact on the ecosystem. And this is why, for instance, on the Po River, they decided not to build any barrage beyond Isola Serafini. The Po River is equipped with only one barrage, whose main purpose is to produce groundwater, which is to produce hydropower, which is the centrale of Isola Serafini. And in the Po River, we try to avoid building barrages in order to preserve the quality of the ecosystem. Okay, let me see if I think I have a link here that explains how navigation locks work. No, it's not here. Okay. Anyway, let's forget about navigation locks because it's out of our purpose. Okay, so let's focus on river barrages and water diversion by means of unregulated infrastructures. And with the term unregulated, we mean that there is no automatic regulation of the upstream water level. There is some regulation, as we will see here, in these barrages which are called unregulated. There are still some gates that can be opened and closed, but the main purpose is to interrupt the water diversion under certain conditions. The main purpose for putting gates there. And the main purpose is not to regulate the storage and water level upstream. Okay, now, these barrages are, as I mentioned before, typically built, typically realized for producing hydropower. And in particular, they are widely used for run-of-the-river hydropower plants. Run-of-the-river plant, we already mentioned what it means. It means that we get water from the river when water is available without any storage. And they are called in Italian impianti ad acqua fluente, which means literally plants for flowing water, not for stored water. But in English, they are called run-of-the-river hydropower plants. Now, the first problem that we need to solve when we design a barrage for water diversion is to estimate the design flow. Whatever the purpose is, because keep in mind that I'm talking now, I'm making mention frequently to hydropower plants, but there are barrages that are also realized just for withdrawing water and deliver this withdrawn water to water supply systems, irrigation or civil use. But whatever the purpose is, our first problem is the assessment, estimation of the design flow. But we know how to solve it, because we already dealt with indirect and direct methods for inductive and deductive methods for assessment of water resources. We know that when we can use a flow duration curve, we use the flow duration curve, and we know that we can use models if we don't have observations or if we have only a limited amount of observations. So this is a problem that we already solved, and therefore here you have a couple of sections that are dedicated to the flow duration curve. And also here you see a mention to the water withdrawal index and the water use index. We already discussed them. Okay, so we don't need to specifically focus on these problems. And what we need is to focus on the other design problems related to the sizing of the barrage structure. And we will not focus on the structural design of the infrastructure, but we will focus on what we call the hydraulic behaviors, and therefore what is the elevation of the structure and what is the level of the various and the functioning of the various weirs that we need to realize in order to withdraw water and in order to allow the excess water to flow downstream. Remember that these structures are designed, as I said, to withdraw water for whatever purpose. But we have to limit their impact on the river. And therefore, we have to make sure that we have facilities for withdrawing waters and facilities that allows us to make sure that water can flow downstream, excess water can flow downstream with a limited impact. So we will have a design flow, which is the amount of water that we need to withdraw, and then we will have an excess flow, which is the flow that will be not always there, will be there typically during high flow conditions, the flow that exceeds the amount of water that we need to withdraw. So we will talk about withdrawal flow, and excess water. Let me open this picture and enlarge it because it clarifies what is the typical structure of a river barrage. Let me see if I can. I need to resize it because, okay. Not very clear, but let me check if I can do it another way. No, this way. And 4. Just 1 second. Okay, I think this is fine. Okay, so we have the river flowing from the left to the right, and the typical structure is given by a transversal wall, and in this case the wall is placed perpendicularly to the main direction of flow. But in some cases you may see the structures that are displaced at an angle, and the reason may be that you want to make longer the length of the wall. So in order to make it longer, instead of putting it perpendicular to the flow, you may put it at an angle in order to have more space available. And the reason is that sometimes we need to put also facilities in the body of this transversal structure. In this case, it is displaced for simplicity. This is a very simple sketch, perpendicularly. And we have what is called a main spillway, which is the spillway or weir, you can call it weir or spillway, over which there is the excess water flow, and this main spillway should be designed in order to allow the flood flows to pass through without causing a significant increase of the water level upstream. How to do this, we will see later, okay? Typically, there is a central part of the main spillway that is placed at a lower level. The reason is precisely what I mentioned before. We want to keep the main flow quite far from the hill slopes, at a distance from the hill slopes. Of course, this central part shouldn't be too much restricted, because if it is very narrow, then we cause an increase of the flood level upstream. So we have to seek for a compromise, the compromise between our need to keep most of the flow far from the hill slopes and the opposite need of not to make this central passage, this central spillway, too narrow. Here you see with these particular distinction signs the parts that are tilted that connect the central part of the spillway at a lower level to the lateral parts which are placed at a higher level, and therefore you get, if I look from the front, from downstream to upstream, if I try to design, to reproduce this structure by looking from downstream to upstream, I will see this wall here, and then there is the weir that is done in this way. I limit it to the right part, and actually, if I want to reproduce what is depicted there, it's like this. Okay, and this is the central part of the weir. In Italian it's called gavetta. There is no translation of this term in English, and these parts connecting the gavetta with the lateral walls are called wings. The wings have typically a slope of 100%, 45 degrees. Now, what happens on the left part? On the left part, I have another wing here. And before getting to the this wall, to the wall that is placed on the left. I have here, in this picture, another weir, and then I get to the wall. What is this second weir? It's called, this is the environmental flow weir or spillway. It is placed at a lower level. What is the reason why this weir, which is the weir that is in charge of allowing the environmental flow to flow downstream? What is the reason why it's placed at a lower level? Because we want to give priority to this flow. We want to make sure that the environmental flow always flows downstream. Keep in mind that the environmental flow must be always ensured. And therefore, it has to be placed at a lower level with respect to the excess flow spillway. Typically, we have here downstream the environmental flow spillway. We may have a fish ramp, which is not depicted here. I didn't put the fish ramp here because it would make the sketch too complicated. But typically we have here a fish ramp. Now, what's missing on the blackboard is the set of the diversion facilities. In this sketch, diversion is operated laterally, lateral diversion, which means that there are diversion spillways that are placed on the side of the structure, and they must be placed at a proper elevation. Proper elevation because our purpose is that this plant works automatically without any regulation. As I said, and we will see, there are some gates that are put there, but only with the purpose of occasional maneuvering, for interrupting the flow, for cleaning, for maintenance, etc. It's not a continuous maneuvering of these gates. So it's clear that if I want that this structure works without any regulation, because it's an unregulated barrage, it's clear that I have to make sure that the various spillways are placed at an altitude that allows an automatic operation. They need to be placed at an elevation in order to make sure that everything works for gravity. Therefore, I already mentioned that the environmental flow spillway has the lower elevation. But then, if from the environmental flow spillway I increase my elevation, then I have to find at a higher elevation. The next spillway is the diversion spillway. The diversion spillway must be placed higher with respect to the environmental flow spillway, but at a lower level with respect to the main spillway. Because I want to make sure that before releasing excess water, I have diverted the design flow. Therefore, if I want to put my diversion spillway here, I will put it, or let me make it clear, at a level that is between the level of the environmental flow spillway and the level of the main spillway. So when water gets against this barrage, first, water flows through the environmental flow spillway. If there is enough water, you see the environmental flow spillway is not very large, it's small. And therefore, if I have an increase of flow from upstream, as a result, the water level will increase because the environmental flow spillway is quite small. And therefore, the water level increases and reaches the level of the diversion spillway. And therefore, I start seeing some water that flows through the diversion spillway and goes to distribution through a series of facilities that we will carefully discuss. Then, if I have enough water from upstream, let's suppose during a high flow period, then I still will observe an increase of level upstream because these spillways, environmental flow and diversion spillway, are not very large, so water will accumulate upstream and may reach the level of the main spillway, especially during floods. And therefore I will start seeing some water from the main spillway, which is very large because I need to make sure that the flood flows can flow downstream without any problem. So I hope it's clear to you the sequence of the levels. First, environmental flow spillway. Second, diversion spillway. Third, the main spillway. And now we can indicate with delta H1 the difference in elevation between main spillway and diversion spillway, and I can indicate with H2 delta H2